work through an example of an equilibrium structure. We have a ladder with a person on it. The ladder makes an angle of 50 degrees with the horizontal direction, and the ladder is up against a smooth wall. We want to find the forces exerted on the ladder such that it begins and remains at rest. So we're given some information. So let me record that. So we're given the person on the ladder, the firefighter, and they have a weight of 875 newtons. And they are 6.3 meters up an 8-meter ladder. And we're also given that the weight of the ladder is 355 newtons. Okay. I'm going to pick a couple things first and use those consistently as we go through and solve the problem. So I'm going to pick coordinates where x goes to the right and y goes up the page, and I'm going to place my rotation axis at the point of contact between the ladder and the ground. And the reason I want to do that is that's going to immediately eliminate the torques from the force that the ground exerts on the ladder. So my torque equation is only going to have one unknown in it by design. So I put my rotation axis in, and the sense of a positive rotation is one that goes counterclockwise. Now, the ladder begins and remains at rest, so it's an equilibrium. It's going to be an equilibrium for any possible choice of rotation axis that you make. So I was just picking one that's going to make my work a little easier. So the weight of the ladder is a force exerted on the ladder, and that's going to be halfway up. So let me draw that in. The person on the ladder, if they are in equilibrium, then they have a contact force that the ladder exerts on them that's enough to cancel out their weight. So that force of the person pushing down on the ladder is a force on the ladder. And that's going to act straight down. The ground is going to exert a normal force to hold the ladder up. So I'm going to call that force G, and it's the y component. There's also going to be a force of friction that the ground exerts on the ladder at that point of contact. I'm going to pick that to go in towards the wall. I do that because the wall can only exert a normal force, and I know that's going to have to point away from the wall. So if I picked the positive direction for the x component of G to be away from the wall, when I go through my equations, I'm going to find out it points in the opposite direction, which is fine. Just go ahead and try to get the signs right to begin with. And then the wall is smooth, so all it can exert is a normal force. There's no force of friction that the wall can exert on the ladder. And in fact, if there were a frictional force that the wall could exert on the ladder, I would have 1, 2, 3, and then that frictional force would be the fourth unknown. So that would already make it be an indeterminate structure. I wouldn't have enough equations to solve for the 4 unknown forces. We'd have to break the system into 2 parts and invoke Newton's third law for how those pieces push equal and opposite to one another to have enough equations for the 4 unknowns. All right, so just make a little notation. Gy is the normal force from ground on the ladder, G of x is force of static friction from ground on the ladder, and N is the normal force the wall exerts on the ladder. Okay, so those are our three unknowns, and we know we have three equations available to us to solve this. So I know I add up all of the forces that act on the ladder on both of the coordinate directions, and those have to sum to 0. And that's going to give me two equations. And then I also know that the sum of the torques about the rotation axis that I picked also have to equal 0. So that's one equation. So should be able to solve this. I have 1, 2, 3 unknowns, and I have three equations. So let's go ahead and get started. If you look at equilibrium acting left and right, that's the condition that all of the x components of the forces sum to 0. For that, I have one component, gx, in the positive direction, and I have one force, n, in the negative direction. So that tells me the x component of the ground's force minus the normal force is equal to 0, or the x component of the ground force is equal to the normal force that the wall exerts. So I don't know either of those yet, but as soon as I know one, I immediately know the other one. Okay, so that's one equation. Next equation that we can use is that I add up all of the y components of forces, and those will have to sum to 0. I've got a few more of these. There's the y component of the ground force, that's in my positive direction. I have the weight of the ladder acting down, it's my negative direction for y, and then the weight of the firefighter due to the firefighter's contact force on the ladder. And that has to sum up to give me 0. So I can rearrange that. The ground force is going to equal the weight of the ladder plus the firefighter together, which that's 875, 355, 1230 newtons. So that one's already done. Okay, so gx isn't known yet, the normal force the wall exerts isn't known yet, and we have one of those three unknowns solved. So for torques, I have picked my rotation axis here at the base of the ladder. So line of action for gx goes through the rotation axis, so that causes no torque. The y component of the ground force, its line of action goes through the rotation axis, so that causes no torque. So I'll just have 1, 2, 3 forces that cause torques. And go ahead and make some notations for what these angles are. If the ladder is inclined at 50 degrees to the horizontal, then I know that angle between the ladder and the weight of the ladder is 40 degrees. this one is also 40 degrees, and if this angle is 50 degrees, so is this angle. And in terms of the position vector for those three torques, the weight of the ladder acts at half the length of the ladder, the weight of the firefighter acts at that 6.3 meters, we were given that, and then the normal force acts at the entire length of the ladder for its torque. So let's write out the torque equation and try to solve for the normal force then. That's going to be the only unknown for that choice of the rotation axis. So we've got, add up all of the torques. There's going to be 1 due to the weight of the ladder, torque due to the weight of the firefighter, and then a torque due to the normal force from the wall. And if the ladder begins and remains at rest, it doesn't start sliding, then those torques all have to add to 0. So for the torque caused by the weight of the ladder, that is trying to make the ladder rotate clockwise, so that's a negative torque. So I'm going to have a minus 4 meters times the weight of the ladder times sine of 40 degrees. The firefighter is the similar looking expression, except they're at 6.3 meters and they have a different weight, but it's also sine of 40 degrees. And then we have the normal force, which the normal force is causing a torque that's trying to make the ladder rotate counterclockwise, so that's our positive direction. So that comes in with a plus sign for its torque of 8 meters times the unknown normal force times sine of 50 degrees, and that all has to equal 0. So not a beautiful equation, but it does have only one unknown, this normal force. So let's go to another sheet of paper and solve for what that normal force is. So rearrange it to have only the unknown normal force by itself. We have the torque from the weight of the ladder, and that's times sine of 40 degrees, and the torque from the firefighter, and they have a weight of 875 newtons, and that's also sine of 40 degrees, and that's all divided by the length of the ladder, 8 meters, and that is sine of 50 degrees. And you go through and calculate that, find that the normal force is 727 newtons. And then from our condition for horizontal equilibrium, we know that that's also equal to the force of static friction that the ground exerts on the ladder. So that's also 727 newtons. So a slight variation you can make on this problem is, instead of solving for the force that the ground exerts, its normal force component and static friction force component, you could ask what's the smallest value that the coefficient of static friction could be for the ladder to begin and remain at rest. And there we go. We got all three unknowns solved for. And most of the work in doing an equilibrium structure problem is in setting up the free body diagram. So that's the part that often needs the most practice. You need to account for every force that's acting on the object, and then you can simplify your work by picking the rotation axis to be at a location that'll eliminate some of the torques. So you have less work to do, less substitution between the three possible equations. And then if you have more than three unknowns, once you're looking at your free body diagram, you know immediately it is an indeterminate structure. You're not going to have enough equations to solve for all of them. So you'd have to break the object up into multiple parts. And imagine like the bottom of the ladder could move relative to the top. And that would introduce a force that the two halves exert on each other at that midpoint, for example. So think carefully about the free body diagram when you set it up, and then use our three equations.